Всем доброе утро. Народу еще немного, давайте подождем пару минут еще. Скажите, меня слышно, презентацию видно?
Да.
Доброе утро, все хорошо.
Ладно, давайте решим, что те, кто хотел проснуться, уже проснулись. Смотрю, количество не увеличивается, по-прежнему 7. Давайте начнем сегодня. So this lecture is going to be about a special subject, which is rather special but extremely important for superconducting quantum devices, and not only for them. It's important for many nanoscale devices, for nanomechanical devices, for a variety of solid-state systems where material defects can influence the macroscopic performance. So we are currently at the end of our course. So today we speak about the origin of decoherence, about two-level defects in the first lecture. And in the second lecture, we primarily will talk about qubit readout, and I will briefly mention state of the art about quantum processors and simulators. All right, so decoherence. Decoherence means the property which sounds negative. So one can turn it around in positive with the coherence, but what limits the coherence is decoherence. Back into the history of superconducting qubits, in this plot, which actually is almost 10 years old, you see that in the first roughly 15 years, since the demonstration of the first superconducting qubit, the qubit lifetime, which means T1 time, the relaxation time from the ground state to the excited state, has been growing up very rapidly. And we discussed already various devices. We discussed Copper box, which is this CPB point here. We discussed the Pantronium device, where there was a double sweet point in charge and flux, which was significant improvement. And then with arrival of transmons, and then three-dimensional transmons, the coherence time was going up and up. And people even used to call this kind of Moore's law of superconducting qubits, so that the T1 time was actually increasing almost in exponential law. So you see on the left, this is logarithmic scale from starting from 1 nanosecond and then extending to a millisecond. And then there is a point, even few milliseconds. This is about 3D cavities, which I briefly mentioned in the previous lecture. So this Moore's law, or quasi-Moore's law, actually did not hold. In the last 10 years, the coherence time of superconducting qubit improved a little bit, but not really much. So the coherence of the order of several hundreds of microseconds, which was a kind of record that time for three-dimensional transmons, became more or less normal for planar two-dimensional transmons used in modern superconducting quantum computing architectures. But the record times, they stagnated around millisecond or even below that. And there is a very fundamental reason for that, which we are going to discuss in this lecture today. This is yet another plot, which is from more recent review. Again, you see on the left in logarithmic scale, also starting from nanosecond. At the bottom, extending to a millisecond on the top. the very same points, but there are a few more points added up in the last decade. And you see that actually the saturation tendency, which I just told you, discussing the previous picture, is fully confirmed. So the coherence times don't go up. Moreover, if you try to include additional functionalities in superconducting devices in quantum circuits, then you have to compromise. And very often this compromise goes at cost of coherence. For example, if you want to have more control or better control of the qubit, you need to have more clear readout. You need to couple the qubit stronger to the environment. And this you can only do by sacrificing the coherence time. Simply the qubit becomes less protected. So the compromise is somewhere in the middle. So you need to have some reasonable quality qubit, which would allow sufficient number of quantum operations, but at the same time you want to control it. So let me remind you what are the types of the coherence. What are the manifestations of the coherence? On the left, you see the picture of the Bloch sphere, which we discussed multiple times in this course. And here in the Bloch sphere, we describe the state of a qubit by a vector, which can point in some arbitrary point on the sphere. Now, once we talk about the time t1, it corresponds to the process which is called longitudinal relaxation. Longitudinal means longitudinal along the z-axis. And this relaxation basically leads to losing the magnitude of the, not the magnitude, but the value of the projection on the vertical axis. If you start from state 1, for example, in this plot, it is below here, as often done in quantum optics. Then this is the excited state below. Above is the ground state. I'm discussing now the plot B, but my mouse is for some reason frozen. Then the process leads to exponential process of losing the probability of measuring the maximum projection of the state to z-axis. So if you are pure state 1, then you measure that you are on the south pole, but once you wait for some time then and measure many times to get statistics, then the probability of being in the excited state drops down exponentially. This is the basically the relaxation, which means exchange of energy with environment. So you may eventually emit a photon in the environment, and then this would correspond to the transition of a qubit from excited state to ground state. Another process which we also discussed is dephasing, and that one is characterized by time t2, or correspondingly the inverse time, which is the rate. This is the relaxation rate, gamma 2. That one is associated with the fluctuation of the energy level separation between ground state and excited state. And if this happens, even in the absence of relaxation, the state of the system is not preserved. So basically you will be making kind of diffusive motion along the z-axis, along the equatorial plane. So the rotation around the equatorial plane will be then the dephasing process. And here people distinguish the two times. Actually, one is the pure dephasing, which is due to this fluctuation of the energy level. However, there is a fundamental limitation to the time t2, which is due to the fact that it cannot be larger than twice t1 under assumption of the white noise. That's something which is relatively easy to show, and I think you can look up the textbooks how to do this. But in fact, the relaxation rate gamma 1 consists of the processes which are gamma relaxation time gamma 2 consists of two contributions. One is the relaxation limited time t2, which is gamma 1 divided by 2, and then a pure dephasing time gamma 2. So these are basically the two times gamma 1, or two rates gamma 1 and gamma 2, which characterize the influence of noise on superconducting qubits. And to measure gamma 1, this is a short reminder, and gamma 2, you can, for example, use pi pulse to excite the system from ground state to the excited state, and then delay the measurement of the projection on z-axis. This will be basically showing this exponential decay from 1 to 0, which is sort of turned around here compared to the previous plots I showed. And then if you want to measure the time t2, then you apply pi over half pulse to bring the system to the equatorial plane of the Bloch sphere. And then you let the system evolve over time, which you, of course, vary. And then once you apply in the middle, the pulse, pi pulse in the middle, which will be the echo type recoiling process, then the system will start rotating back under the influence of the same type of noise. And this decay will be exponential. So this sort of cancels out the low frequency contributions to noise, but nevertheless measure kind of pristine time T2, which is at maximum, at the worst case, limited by T1, which will be then twice T1. So all that we already discussed. This is another picture how to measure the time T2, but I think we already talked about this. I will leave it here just to mention that if you measure the Ramsey fringes without this pi pulse in the middle, then exactly on resonance, you measure the exponential decay characterized by T2. And if you tune a bit away from the resonance, then you see the oscillations. And the oscillation frequency is simply a difference of the driving frequency, the frequency of the driving field, and the pristine transition frequency between the ground state and excited state of the qubit. There are different ways to suppress those errors. So one can use the echo, but it's not only echo. One can use multiple echo pulses, and this is the so-called CPMG after Kerr, Parcel, Mai, Boom, Jill. Sometimes people call this bang-bang control. Sometimes simply call it multiple recoiling pulses or refocusing pulses. Basically, repeating these pulses many times cancels a particular frequency range of noise. And if your noise is not wide, but has some specific frequency components, then by choosing the repetition time and choosing the number of pulses, you basically will increase the filtering kind of the qubit. So by doing this, of course, you waste some time by this manipulation, but at the same time you cancel particular frequency contribution of into noise. All right, so this is all techniques which are very widely used, for example, in nuclear magnetic resonance. When you go to computer tomography and the clinicum, then the machine which does the image of your body uses multiple pulses, recoiling pulses, to measure particular spin states and their relaxation, their dephasing. So this is something which is used as a contrast of NMR measurements, which is very useful, of course, for medical investigation of living tissues. Now let's talk then about the mechanisms which are responsible for these decoherence processes in superconducting qubits. And thinking about this as a physicist, we can guess that there could be many different mechanisms. There could be, for example, charge noise, which we already discussed, which is in particular is very important for charge qubits, which are not protected by any inductance shunting the Kappa-Pera box. Then in the case of flux qubits, there will be obviously magnetic field noise, which can be either external noise due to bad coil or bad current source, which will have some noise contributions. But this could be also some magnetic noise due to the parasitic spin states in the material. In particular, on the surface of the material, there are some adsorbates, and these adsorbates contain some uncompensated spins. And these spins can move randomly and contribute to noise. So, for example, in devices which are most sensitive to measure magnetic fields and magnetic field noise, in devices like SQUIDs, the noise is always limited by roughly 10 to minus 5, 10 to minus 6 of the flux quantum. Interestingly, it's independent of the area of the squid, it's independent of the material. It's kind of very fundamental limitation of the noise in squids. And this has been really subject for many investigations in the past. The physics of noise in squids is largely similar to the magnetic noise in superconducting qubits, and still being a subject of intense investigations. So, all right, there are, of course, other types of noise sources which could be in the substrate. For example, if you have some phonons in the substrate, these phonons carry energy, and they can break the Cooper pairs and produce quasi-particles in the material, and quasi-particles will induce additional dissipation. So there are many different ones, but there is one dominating source of noise, which is due to a very specific type of defects, which have very generic properties. They appear in any kind of, practically in any kind of material. And these defects are so-called two-level systems, or two-level defects. What is that? Imagine you have on the surface of a superconductor, you have some oxide layer, or you have some adsorbates. Or if you have a tunnel barrier of the junction, then this tunnel barrier consists of aluminum oxide. But this aluminum oxide is not ideally perfect crystal. It's an amorphous material, which is formed by oxidation of aluminum on the surface. And in any amorphous material, on any disordered material, or in any adsorbate layer, which is not ordered on the surface, there will be some irregular positions of atoms in the structure. And one can imagine a situation when very seldom, randomly, there will be some locations for an atom or a group of atoms, some locations nearby. For example, you have two local minima of energy for an atom to be either in position which is indicated by green dot here, or in a position indicated by red dot. And this atom can be either in one position or the other. Since atom is a very light object, it can tunnel between two positions. And in the presence of disorder, there will be a whole range of different states characterized by this kind of double potentials, where the tunneling energy will have a very broad distribution. So the energy of an atom sitting in a lattice, as you know, is in the range of electron volts. Now, what we are talking here about is the energy scale, which is roughly 1,000,000 times smaller. So it's not the binding energy of an atom in a crystal, but it's much smaller energy, which corresponds to the process of atom tunneling between two neighboring locations. And this kind of states are have been speculated in the past to exist in glasses, but now they are investigated in many different situations, and they are found on surface oxides, they found on the substrate, they found at any kind of interfaces, they found also in tunnel barriers of the junctions. And they generate noise and dissipation not only in superconducting qubits, but also in other small-scale devices, electronic devices like transistors, like nanomechanical and micromechanical resonators. They're important for single photon detectors, for superconducting resonators, and so forth. Even gravitational wave detector, which you know is a large instrument which led to observation of gravitational waves a few years ago, actually 3 years ago. That instrument consists of specific mirrors which are covered by dielectric. And this kind of defects in the dielectric actually are the origin of the limitation of this huge instrument, the origin of noise, which limits the accuracy of this gravitational wave interferometer. So that's something which is really very fundamental and is characteristic for any kind of primarily dielectric material. And specific nature of these atomic states is still being discussed, debated. There are different theories. What are they? people think that this could be hydrogen atoms adsorbed from the surface. This could be some dangling bonds. This could be some electrons trapped in interfaces. There is a recent theory about the quasi-particle nature of these defects in superconducting qubits. This could be some dressed states of electrons with other degrees of freedom in a crystal. This could be simply tunneling atoms, which I just described to you as a simple approximation. What it is exactly, actually, it's not known, but it's not impossible to speculate about several different origins, different species of these two-level defects in materials. Now, imagine now that you have those defects somewhere. This could be either a single atom or, as I said, a group of atoms undergoing transitions between two configurations. Once this transition happens, then naturally the local electric field and also mechanical strain changes. And each defect can be characterized by some effective electric dipole moment, which changes as the system goes from one state to another. Classically, we have now a picture, which is the picture I showed you in the very first lecture when we discussed which we discussed qubits compared to the classical states 0 and 1. I gave you an example of a double well potential where we allowed for tunneling between the ground state and excited state. Tunneling between the left well and right well, forming the superposition of the two states, left and right, and characterized by the ground state, which is shown here by green line. This is the probability amplitude, and the first excited state, which is shown here by the red line. So basically, this is a two-level system which we know to exist as a qubit. However, the single atom tunnel between two locations in the crystalline potential will have exactly those properties of a double well potential. And looking back into textbook, you can find the two-level system has the energy level separation, which is given by this formula, where delta is the energy level separation for symmetric potential. So when two wells have the same depths, then the frequency of the transition between the ground state and excited state is going to be minimal and equal to delta. And once you make the potential asymmetric, then the energy level separation increases, and it increases as a square root of epsilon square plus delta square, where epsilon is the asymmetry of the potential. So basically, the epsilon is the difference in energy between the deepest well and the neighboring well. So this is a very generic textbook formula, and this functional dependence is actually hyperbola. So this hyperbolic dependence of the energy level separation should be characteristic to any kind of two-level systems. Now, two-level system is described by the Hamiltonian, which you see here on top. So this, the Hamiltonian is written here in notation of Pauling operators, sigma x and sigma z, where delta is the amplitude in front of sigma x and epsilon is the amplitude in front of sigma z. And the asymmetry parameter is some intrinsic parameter, which is due to the eventual structure of the material there. But you could also contribute into this z by applying either electric field or strain. So by applying strain to mechanical dipole, you would change the energy states in the double well potential. And the same appears if you apply the electric field. So you basically can influence the asymmetry by applying external fields, in particular electric and strain fields. Influencing the tunnel barrier between the states is in the first order, or maybe even in the higher order, is not relevant, because this barrier height is given by the material itself and not by external fields. So this is basically a local structure of the amorphous material at the location of the two-state system. So basically, we note here that these states should be depending on the locally applied fields. And the initial hypothesis about the importance of these microscopic states for superconducting qubits came about very early. In the very first experiments of the group Martinez group in Santa Barbara with superconducting qubits, which was actually, I think that time John was still even at NIST, but he moved to Santa Barbara around 2005, 2006. So in the very first experiments with phase qubits, people observed very peculiar property showing that the tilted cosine potential, which is expected to have a very smooth dependence of the energy level separation on the tilt, shows some interruptions in this dependence, which have a very characteristic shape of the avoided level crossings. If you couple two quantum systems together, then even couple two qubits, then you have the repulsion between the levels, so there will be symmetric and asymmetric state formed. And if your two-level system, superconducting qubit, interacts with another two-level system, which could be either macroscopic or microscopic, then there will be avoided level crossings once the frequency of those two systems is the same. And here you see on the left plot, left bottom plot, the frequency as a function of the tilt, which is the flux bias of the phase qubit. And instead of having the straight line, the contrast here is the probability of measuring the system in the excited state. So once you apply microwave field in resonance, then you have this red line in the blue background, which is basically no excitation. Then there is a particular interruption, which you see here, shown by this dashed line. And this is exactly what is called avoided level crossing. So instead of two frequencies for the same flux, one frequency in the same flux, you see two frequencies at the fixed flux. And this corresponds to interaction with something which has the same frequency. Then there is another avoided level crossing below, which you see here. And when looking at the dependence of the time t1 as a function of frequency, actually one observes here very specific interesting feature. So one observes here two large effects at these two frequencies, which are indicated here. This is this red line here, and then the line where my cursor is now, or my pointer here is below. So that's where you really see the avoided level crossings. But in addition to that, there are also some points which are not very well seen here because they don't show the avoided level crossing. The avoided level crossing has the line width, which is smaller than the line width of the qubit itself. But nevertheless, there is a particular frequency at which the lifetime of the qubit is much shorter than at neighboring frequencies. So shorter time corresponds to this blue color, which extends more to the left in this plot. And this particular property actually was a kind of fingerprint of a qubit. So what they found in the first study is that if they warm up the sample to room temperature and cool down the sample again, the positions of these frequencies was changing. So this was not really something in the environment, something which was defect of the circuit, but this was really something which depends on the properties of the material. Of course, if you warm up the material, then some of the configurational states of atoms may change due to thermal fluctuations. And once you freeze down, then everything is in new configuration. So this was really a very interesting observation at that time. And now we know that it has been already more than 10 years, or about 15 years of studies of these defects in superconducting qubits. And I should say that my group in Karlsruhe really contributed to that with a number of very interesting discoveries. So we know now that these defects are formed in the tunnel barrier of the junction. They are formed also on the surface of superconductors. They are formed on the surface of the substrate. They can form in the oxides, which are formed once you take the aluminum film into the atmosphere, and many other locations. This could be adsorbates, this could be residuals, this could be contaminates, and so forth. And again, what exactly is tunneling is not very well known. You see on the right a lot of different propositions what is tunneling there. There are some experimental works showing that, for example, molecular oxygen or hydrogen states can be responsible for some of those defects, but not for all of them. So this is really a kind of intense field of research. But the whole field started from old papers. Let me see if I have some. No, I don't have it. I can tell you by words. Actually, in the 70s, there was a very interesting discovery that experimentalists measuring glasses at very low temperatures, they found specific heat, which is much, much larger than specific heat expected for a crystal. And then the proposition was that there might be some degrees of freedom which have very low energy level separation, very small in the range of micro electron volts, such that these degrees of freedom are saturated at high temperatures, but at low temperatures they're not saturated, and therefore they can also absorb heat. And then there was a theory by Phil Anderson and Phillips, two parallel papers about the same time, around 1970, where they put forward the idea of these generic two-level systems which exist in any amorphous material and in glasses. And then there was a lot of work in the past trying to find the effects associated with these ensembles of two-level systems with very broad frequency distributions, which actually have the influence on many properties of solids at low temperatures, such as specific heat, thermal conductivity, ultrasonic attenuation, sound velocity, and so forth. So this is really a topic which is not new and appeared in superconducting qubits only for the reason that in superconducting qubits, for the first time ever, one can really see these defects one by one, not the ensemble of defects like people observe in glasses, but really individual defects leave their fingerprints in the spectra of superconducting qubits. And these defects are responsible for a variety of noise phenomena in superconducting qubits. So when people started doing systematic measurements on superconducting qubits, they actually found that everything is much more complicated than one can think. For example, you see here 3 papers. I don't have more updated references. They all were published, I think, in PRL, except for one of them. So the top work is the work from my group, where we looked for the long time dependence of a relaxation in a superconducting transmon qubit. And this, if you simply continue measure applying pi pulses relaxation time, in average you measure some time. Let's say in this particular case it was around 100 microseconds, and you see that this time starts changing. Not only time starts changing, but also the frequency of the transition between the ground state and excited state also starts changing. So this plot shows the shift of the transition frequency up from 0 to 1 as a function of time in hours. And you see something is happening after some hours. There are some jumps, some increases and decreases. There are some telegraph switches. Now the Chalmers group, this is this work, they measured very similar time scale fluctuations of the time T1. And this is the work done a little earlier by the Google team, where they looked for the T1 dependence of on frequency, actually measuring very different profiles after 15 minutes of separation. So all this kind of observations led to hypothesis, which is widely accepted now, that the origin of this fluctuation is due to some two-level defects which have very small energy level separation. So the tunneling time between the states is going to be quite long, much larger than the coherence time of the defect. And therefore, this defect will undergo transitions between two wells very randomly under the effect of thermal fluctuations or eventual tunneling. But if this defect is elastically or electrically coupled to another coherent defect nearby, this would strongly influence the properties of a qubit, which in turn seems the coherent defect. So if one defect has energy level separation in the range of kilohertz or megahertz, and then fluctuates between two states, this particular defect can influence the other one, which has energy level separation at the frequency range of the qubit. which is naturally coupled to this defect by its electric field. So in this case, shifting the frequency of this coherent defect closer to qubit resonator, as you see on this cartoon on the left, will influence the times T1 and also T2 of superconducting qubits. Now, all these hypotheses, they have been confirmed by many experiments, and really putting the numbers into simple estimate how large should be electric field, which should influence this defect, how large should be the coupling between the microscopic defect and superconducting qubit, actually came up with very convincing estimates, which I will probably not discuss here, but that's something you can think about. What will be the dipole moment of a electron charge shifting by 1 angstrom? So this will be roughly the value of the electric dipole. And if this dipole is sitting in the tunnel junction, which has separation between superconducting electrodes of the order of, let's say, 10 to 20 angstroms, then this very tiny charge will produce the electric field variation in the capacitor of the junction, which will couple to the electric field induced by the plasma oscillations of the junction, which, as you know, are the oscillations characterizing the states of transmodes, for example, over charge qubits. And similarly, there will be also possibly magnetic interaction, but magnetic types of magnetic defects have been reported only few times and not really observed systematically until now. Now, how can we make sure that these defects are really there, that they are microscopic? How can we make them, what will be the smoking gun, so to say, about those defects? The experiment which was done in my group back 10 years ago was the following. So we took a chip with superconducting qubit, and we fixed it with this clamp, as you see, with this kind of U-shaped holder. So the qubit is here on top. And then at the bottom, we put a piezo drive with little zircon ball in order to apply some tension, mechanical strain at the bottom of the chip. So if you shift the center of the qubit chip by 1 micron, then the distance between atoms in the structure changes very little, and it's roughly 10 to minus 7 per volt relative change per volt of the piezo drive applied to this qubit. And it's very tiny displacement. So if you think of the scale, if you have 1 nanometer distance between something in the material, then the compression of this 1 nanometer will be as small as the size of nuclei. Actually, it's even smaller than the size of the nuclei. So it's 10 to minus 16 relative to 10 to minus 9 meter. But that very tiny change already corresponds to quite a large mechanical strain and large also dipole field, which may be induced in the material. And by doing that, one can influence this parameter epsilon of the asymmetry of the double potential such that one would be able to vary the frequency of the defects. And this plot shows you beautifully this hyperbola of individual defects. So this plot is actually a first time ever observation of the signatures of individual defects in amorphous material, showing the dependence of their frequency on the applied mechanical strain. So this is the piezo voltage, which is proportional to the strain, which is in turn proportional to this parameter epsilon on the horizontal axis of the above plot. And then the frequency of these defects, which is shown here by these black dots, clearly has the shape of this multiple hyperbola, which is a very generic remind you the hyperbola from above. Of course, there are randomly distributed those defects, and they have very different frequencies. They have very different minimal energy, but the strain actually allows seeing them one by one. And one observes here really a lot of interesting details that each defect has its own particular properties. So some of them have strong coupling to the qubits. They show very high contrast. Some of them very
weak coupling, and they are showing here by very slight lines. There are sometimes shift from one line to another one. There are this telegraph switching between different lines. These are all signatures of interacting defects when they interact with each other. So this is something which is actually present in superconducting qubits, and which limits the coherence of superconducting qubits in all existing quantum processors, Google, IBM, and so forth. They are all suffering from this kind of defects, and the limitation is due to the material properties. Now, the defects have very interesting physics, and this physics can be learned from looking into the spectrum. So, as I said, there is a telegraph switching between the defects. There are also some signatures of coherently interacting defects when two defects, two little dipole, actually interact also directly with each other and not through the qubit. There are also some irreversible shifts which are due to the deformation of the material, which occurs due to applying the mechanical strain. So all that has been studied in great detail. Moreover, more recently, we learned that having those defects here in superconducting qubits makes it also possible to influence them not only by strain, but also by applying electric fields. If the defect is in the surface of the sample, then applying the electric field by a gate, which is simply a piece of metal lifted above the surface, then it influences the electric field on the surface, and these defects will change their frequencies. And this experiment was done, and you see below here, you see a similar picture of the frequency versus the tuning parameter, but now it's not the strain, it is the electric field. And you see that some of the defects show this hyperbolas as before, and these are defects which are on the surface, but some of the defects are not changing their frequency at all. And these are the defects which do not see the surface. This could be defects inside the superconducting tunnel junction. So if you have two superconductors separated by a thin layer of oxide, then these defects are not really influenced by external electric field. Of course, they remain to be influenced by strain, because it's some kind of material, intrinsic material property. So by investigating which defects are influenced by electric field only, and which defects are influenced by electric field and strain, one can sort of label those defects as being defects on the surface or being defects in the tunnel junction. And that's another picture where we shows that the defects inside the junction, they don't really change their frequency. These are these horizontal black lines, while defects on the surface really show this very generic hyperbola, which I already discussed. More recently, we have really done some work which actually helps the technologists to figure out where defects occur. So we could even resolve defects on different surfaces. For example, if you have a piece of aluminum, as shown here, on the surface of the sapphire substrate, it's aluminum 203. This is sapphire. The defects occur on different interfaces. One interface, which in principle is very clean, is the interface between sapphire and the metal. That interface can be cleaned in situ in vacuum by, for example, reactive ion etching before depositing aluminum. Now, once you fabricate the aluminum film, you need to pattern it, and when you take the film out and you pattern, put the photoresist on it, then of course you bring some something on the surface. This could be resist residuals, this could be contaminants, this could be adsorbates, and so forth. So there will be also then defects which occur on the surface of the substrate near the edge of the superconducting film. But there are also defects which occur on the oxide, which is covering the metal surface after it's exposed to the air. And there are also defects inside the oxide layer, somewhere here, which are between the metal and the layer of oxide. And by applying actually two voltages, one voltage gate from the top, the other voltage gate from the bottom, one can sort different types of defect and actually tell which particular interface is having the largest contribution to the density of these defects, to the number of those defects. This can be guessed from doing the electrostatic field simulation of those field from the top and field from the bottom, where on the top surface you predominantly have the field from the top. This is this red arrow, where at the bottom you have predominantly the field from the bottom. Of course, there will be some remaining field effect from the top, but this will be smaller on the lower surface and larger on the upper surface. So doing this simulation and then making kind of generic assumption about the age of the sample, one can actually solve the transcendental equation of the ratio of the tuning rates for the frequencies of the defects, as described here. This is the top field, this is the bottom field. They all both contribute to the electric field on the surface. And then from the map of the ratio of the two fields, one can resolve the allocations of TLS. This was done rather recently by Alex Bilmes, who did PhD in my group, and then he shipped it to Google sometime later. So this allowed for the first time to really have counts of the number of defects on different surfaces. So you see here that on the interface between metal and substrate, this is this red interface, there is only very few defects detected, where when the defects are occurring on the surface of the substrate, these defects are weakly coupled, but they are distributed quite uniformly, and one can count them, of course, with decaying resolution away from the qubit. And the majority of the defects actually occurs on the surface of the oxide. So once you have oxidized aluminum film, that's where amorphous oxide attracts other contaminants and exacerbates, and that's where actually the largest number of defects, in particular strongly coupled defects, are present. Now, this is not the only origin of coherence. So the two-level defects really and loss in dielectrics are limiting the coherence times of superconducting qubits. But more recently, people discovered something which was not really expected at all, which people even didn't think of. Actually, the effect that the number of quasi-particles in real devices, in superconducting devices, is much, much larger in average than one would expect from the thermal equilibrium. So, you know, the quasi-particles are excited states of electrons above the condensate of Cooper pairs, and quasi-particles with decreasing temperature down to millikelvin, their density should really drop down very quickly and drop down exponentially because of the existence of superconducting energy gap. So you need to have to break the energy gap to create a quasi-particle from the condensate. And at low temperatures, you would expect really negligible number of quasi-particles, roughly 2 quasi-particles or 1 quasi-particle, let's say. Of course, they occur by pairs per cubic centimeter of material at 100 millikelvin for niobium, for example. Nevertheless, it turned out that actually the number of quasi-particles is much, much higher. And the reason is the following. When you make experiment with superconducting circuit, of course, you put the circuit in a shielded environment in the cryostat at very low temperatures. However, there are high energy processes, high energy ionizing radiation, which exists everywhere. These are cosmic rays, these are muons, which have very large penetration depths, and they just fly through the Earth. But randomly, they have some scattering events, and these are very high energy particles, which generate, of course, kind of splashes of energy in the materials. So predominantly, they break electrons. They can excite electron states, but they can also excite atomic states, and this generates large energy phonons in the material. And these high energy phonons, in turn, they can have an avalanche of other processes, breaking the electron states, and of course, breaking also Cooper pairs. So this ionizing radiation can be, as I said, either cosmic rays or simply the residual radiation which exists around us. So any concrete wall has a certain intensity of this radiation, which is of course very weak, but it's everywhere on the Earth's surface. And these random events, very high energy events, they generate unwanted quasi-particles, which occur due to scattering of phonons coming from the material of the substrate, for example, scattering of the phonons in the superconductor. Of course, they also can occur in the superconductor, but the volume of the superconducting film is very tiny compared to the volume of the sample holder and the volume of the substrate. Therefore, mostly as a source of this scattering of ionizing radiation, people consider substrates. Now, the impact of ionizing radiation on superconducting qubits is versatile. So you will have, of course, Cooper pairs being broken, and then quasi-particles appearing in the material. And then after some time, these quasi-particles will, of course, have a certain probability to recondense, to relax. However, if you have a small island and you have an odd number of quasi-particles, then this relaxation is simply prevented by the parity reasons. So you need an odd number of electrons to form Cooper pairs in the material if you have a countable number of electrons. And if you have a tunnel barrier with a Josephson junction attached to a small superconducting grain, then of course single electron tunneling through the barrier has to overcome the Coulomb blockade, which energy can be quite large for small capacitance of the junction. So these are the processes which also influence the superconducting qubits, and they were estimated and actually measured by this work of MIT group rather recently. So what they have done, they surrounded the cryostat by a very thick shield, and then they were lifting the cryostat up and down, and then measuring the coherence times T1 at the frequency of the correlated with this position of the setup, either inside the shield or outside the shield. And they found that actually the effect on the modern transmons is there, but it's rather small. So it's certainly smaller than the effect of the two-level defects. However, this type of processes, they influence the superconducting devices. And another example, which was done also in collaboration with our lab in Karlsruhe, was measurements of the quality factors of superconducting resonators in two experimental labs in Karlsruhe and Rome, and then doing the similar measurement in laboratory in Italy, which is located under 1.5 kilometers of rock. This is in Gran Sasso in Apennine Mountain in Italy, where there is a tunnel going inside the mountain to the lab protected by this rock. Initially, it was used for neutrino experiments. So using the natural shield of a rock to absorb various kinds of radiation. But indeed, the quality factor of the resonators measured inside this tunnel was significantly higher than the quality factor of resonators measured outside the tunnel. So these processes are really influencing superconducting qubits. It doesn't necessarily mean that future quantum computers will operate underground. This is most natural proposition, which of course can occur. But it means, in fact, that one has to pay special attention on screening, on protecting the setups with superconducting quantum circuits from high energy ionizing radiation. This is actually an example of events which occur in the superconducting resonators. This is a shift of superconducting resonator frequency as a function of time in seconds. And you see that there are these random events, like huge energy splash occurs in the circuit, and then this energy relaxes exponentially. But then there are those events which occur several times per second, and this is really something which actually also makes the coherence time of superconducting qubits vary. So if you're interested, you could have a look at this, this paper cited here. So since I want to tell you a bit more than the material of the lectures 11 and 12, I will also touch my lecture 13, which I will not read in full in this semester. Let me conclude the story I told you until now today. So the coherence time of superconducting qubits increased by a factor of nearly 1 million over the last 2 decades. But nevertheless, this increase and this progress has been saturated due to the major source of the coherence, which are two-level defects on the surface and in the tunnel junctions. And another important source of the coherence is the ionizing radiation, which generates non-equilibrium quasi-particles, which in turn lead to qubit decoherence. All right, so I want to change this stack of slides, but would invite the questions, please. Задайте, пожалуйста, какие-нибудь вопросы по этой части, пока я не заменил слайды на следующий набор. Вопросы, пожалуйста, кто не спит.
Ну, пока вроде нет вопросов.
Неужели все понятно и прозрачно? Не может быть.
Ну, скорее непонятно и прозрачно, просто нужно будет еще раз лекцию просмотреть по диагонали, чтобы понять, где вопросы.
По диагонали. Ну, хорошо, спасибо за комментарий хотя бы.
Вот вы когда про квазичастицы говорили, вы там вроде начали сначала с какого-то подобия экситонов, а потом там на слайде что-то не очень похожее было, можете уточнить детально?
Почему экситонов? А где вы видите экситон?
Даже не раньше. Не, я просто говорю к тому, что вы вроде начали говорить про экситоны, а потом там что-то другое было.
Нет, про экситоны я не говорил. Экситоны – это связано с состоянием электрона и дырки. Так? Действительно, если вы берете и разрываете куперовскую пару, то у вас образуется электронное состояние, дырочное состояние, такое, что суммарная энергия у них будет больше 2 щелей, вот, но при этом суммарный импульс будет равен фактически импульсу куперовской пары, который равен нулю в отсутствии тока, так? Но в сверхпроводнике, в отличие от полупроводника, дырочные квазичастицы и электронные квазичастицы никаких экситонов не образуют. У них нет связанного состояния. Потому что они находятся, фактически это есть как бы состояние делокализованное, то есть состояние возбуждения, в котором участвует весь конденсат внизу. В полупроводнике такие возбуждения, они локализованы, это называется экситонами. Вот. В сверхпроводнике такого не происходит. Это комментарий насчет экситонов, но продолжите ваш вопрос. В чем был вопрос, который вы хотели задать? Или...
Не, я уже понял. Я вам просто говорил про трудности перевода. Мне показалось, что вы начали сначала про экситоны, а потом я не уловил.
Нет. Фактически, когда прилетает какая-то, скажем, фонон, который имеет большую энергию, он может иметь энергию, оставить энергию, которая будет больше щели. В этом случае, если он рассеивается на конденсате, он выбивает оттуда куперовскую пару, которая производит электронное и дырочное состояние на спектре в зависимости энергии квазичастиц от импульса, например. Да? И эти два состояния, как бы, они существуют при более высокой энергии. Вот. Почему-то у меня мои слайды прыгают как-то без моего участия. Надо посмотреть. Видимо, какой-то тайминг там случайно задан. Еще какие-то вопросы задайте, пожалуйста. Может, кто-то чего-то надумал спросить. Это очень интересная тема. Она вот, в отличие там, от схемотехники и блохотехники, если называть вентили таким интересным словом, это на самом деле очень богатая физика того, что происходит вот в сверхпроводниках что ограничивает когерентность таких сверхпроводниковых схем. Здесь еще очень много всего не понято, и много всего интересного происходит в мировой науке.
А можно спросить, что такое ваттаж плюс?
Значит, это хороший вопрос, да. Это значит, получается, что это есть электронное и дырочное состояние. То есть это есть квазичастицы, две квазичастицы, которые имеют электронный и дырочный характер. Картинку, на самом деле, я взял из статьи, которая приведена ниже. Честно говоря, я внимательно не посмотрел, с чем это связано. Но я думаю, что это именно квазичастицы электронного и дырочного характера, которые возникают из разорванных куперовских пар. Куперовские пары, они показаны здесь синенькие, видите, такие вот два электрончика, объединенные синенькие. Если мы куперовскую пару разрываем, как показано на красной картинке, мы образуем электроноподобное и дырочноподобное состояние в спектре возбуждений сверхпроводника, который имеет две ветви, так сказать, электронную и дырочную. Но если вы посмотрели книжку Шмидта, и мы немножко это обсуждали уже в вводной лекции по сверхпроводимости, в случае, когда мы имеем сверхпроводник, то электронные дырки там не являются как таковыми локализованными объектами, как в полупроводнике. Это есть возбуждение конденсата. И заряд этого возбуждения, он меняется плавно от минус электронного заряда для электронной ветви до плюс электронного заряда на дырочной ветви, проходя через ноль, когда энергия возбуждения равна в точности щели. Вот, поэтому фактически заряд там сохраняется, но он сохраняется суммарно вместе с конденсатом. Вот, это очень важное такое свойство сверхпроводника, которое нужно понимать для того, чтобы не путать электронные дырки в сверхпроводнике с таковыми в полупроводниках. Это совсем другие возбуждения, они происходят в присутствии конденсата, из-за этого они делокализованы. Вот.
И еще такой вопрос, то есть высокоэнергетичное излучение, оно по факту воздействует только на куперовские пары. То есть там на решетку, на что-то еще оно особо не воздействует.
Нет, наоборот. Значит, когда это излучение проникает через наш экспериментальный образец, основные процессы рассеяния происходят в кристаллах, то есть в твердом теле. Это может быть железяка, на которой находится, так сказать, наш образец. И в большей степени важны здесь даже не окружение, которое отделено там механически от кубита, а подложка, на которой он находится, это полупроводниковая подложка, кремниевая или сапфировая, на которой напылена пленка сверхпроводника. Объем этой подложки он гораздо больше, чем объем сверхпроводника, поэтому вероятность того, что такой процесс рассеяния высокоэнергетического излучения произойдет в сверхпроводнике, вероятность мала. А там происходит процесс рассеяния, возникают сильно возбужденные состояния колебаний в решетке кристаллической. Эти колебания – это есть высокоэнергетические фононы. Эти фононы, они в свою очередь распространяются уже по всему образцу, и в том числе дают уже вторичные процессы рассеяния фононов на фононах и фононах на электронов. То есть это фактически куперовские пары, которые разрываются. Они разрываются большей вероятности, что эти процессы происходят из-за влияния высокоэнергетических фононов, которые являются уже вторичным результатом рассеяния высокоэнергетичных частиц. Вот такой процесс. То есть это такой лавинообразный случайный процесс, который происходит, начиная с очень большой энергии и дальше уже меняясь на более низкие энергии во время того, как он достигает всяких дальних закоулков образца. Как-то понятнее стало?
Да.
Хорошо. Если еще есть вопросы, задайте, пожалуйста. Ну ладно, давайте тогда начнем следующий набор слайдов. У нас сегодня будет даже больше, чем 2 набора слайдов. Но как бы это не страшно, потому что последнюю лекцию я все-таки читать полностью не буду, немножко расскажу про нее. И, соответственно, на экзамене тоже мы это обсуждать не будем детально. Ну, там, в общем, скорее даже не материал экзамена, а скорее просто такой обзор того, что происходит в мире. Так, хорошо. Давайте расшарим следующий набор слайдов. Так, видно сейчас? Лекция 12.
Да, видно.
Хорошо. Давайте двигаться дальше. Значит, мы сейчас поговорим еще минут 10, сделаем перерыв от положено через 10 минут. Потом продолжим. Значит, in this lecture, I would like to tell you a bit more about the real procedure of measuring superconducting qubits, namely about qubit readout, считывание кубитов. Now, the key technique which is used for reading out superconducting qubits is dispersive readout. Dispersive readout is readout which is we discussed already, which is achieved by coupling the superconducting qubit capacitively or inductively to a cavity, to a resonator. Now, depending on the coupling strengths and detuning of the qubit frequency from the frequency of the resonator, this readout can be either projective or very weak dispersive, such that the state of the qubit is not destroyed. And this has been studied by many experiments in the last 2 decades, and both regimes have been explored, and many things have been understood. So if you write the Hamiltonian for a coupled qubit resonator system, then which we have done already, discussing circuit QED, then you have here the part which is associated with the resonator. You have a part which is associated with the qubit. This is particular addresses the charge qubit or transmon qubit. And then there is a term which is corresponding to the coupling between those two, between the resonator and the qubit. And here you see the operator, which is number of Cooper pairs charging the qubit. This is the number of excitations, creation and annihilation operators in the resonator. And VRMS is the right mean square of amplitude of the voltage induced in the qubit from the electric field of the resonator. And you see that this the amplitude is proportional to the energy of a photon in the resonator divided by twice the capacitance of the resonator. And the coupling parameter beta is associated with the ratio of the capacitances. In particular, you have the ratio of the coupling capacitor CG to the square root of the sum of the CG plus C and CG plus qubit capacitance. This can be figured out from very easily from calculating the amplitude of the electric fields. And then we already discussed earlier that one can drop the fast rotating terms, and then the Hamiltonian gets simplified going to this James Cummings format, where you have only not 4 but 2 terms after expanding the last term of the coupling, where G remains the coupling strength. And we assume here that the qubit is far away from the resonance, so that the qubit is detuned by a frequency which is much larger than the coupling. And this detuning delta, we basically name the frequency difference between the qubit and the resonator. And then the result of the dispersive approximation up to the second order in ratio of G over delta is that the Hamiltonian is transformed into the form which is easy to recognize to be the contribution of the resonator, which is A prime, A dagger A, and the contribution of the qubit, which is sigma Z. And the frequency of the qubit is shifted by g square over delta, which is the so-called AC Stark shift, while the frequency of the resonator is also shifted by g square over delta, but depending on the state of the qubit. If the qubit is in the ground state and the excited state, then the shift is different. So this is the dispersive shift of the resonator, which is used for the readout. And this is the dispersive shift of the qubit, which can be eventually used to read out the number of photons in the resonator. I will mention this also briefly later on. So these are two coupled systems. One of them is being harmonic, the resonator, the qubit is strongly anharmonic, is a two-level system. And they both interact and have frequency shift associated with the state of the other partner in this interaction. Well, let's first talk about the dispersive qubit readout. Again, that's what we discussed already. If you have a transmission through a resonator, then this transmission, in case of uncoupled qubit, is shown here by this dashed line, gray dashed line. If you couple the qubit, then the resonator frequency changes depending on the state of the qubit. If the qubit is in the excited state, it shifts to the right. This is the red curve. If the qubit is in the ground state, it shifts to the left. And correspondingly, one can also either measure the amplitude of transmission through the resonator, or one can measure the phase of the transmitted signal. In this case, the phase changes by pi when going through the resonance frequency. So, for example, one can have a very large contrast in the readout. If one, for example, stands here in the frequency corresponding to one of the states, then the amplitude changes very large. Or one can stay here in the middle, and then the phase changes very large. So depending on the desired population of resonator by desired number of photons, one can choose the different points and optimize the contrast. For reading out the resonators, the qubits, people use either the transmission line resonator, which is simply a piece of transmission line, piece of coplanar waveguide, which is cut from the central wire here. In this case, you have two open ends separated by two capacitors, C in and C out. And then the electric field is going to be maximized at the end of the resonator. And for the fundamental mode, the field, which corresponds to lambda half mode, which means that the resonator oscillates at frequency which corresponds to the wavelengths twice the length of the resonator. In this case, in the middle, you have the node of the electric field, which means zero amplitude of the AC electric field, and correspondingly maximum amplitude of the magnetic field. So if you couple the transmon or charge qubit, you need to couple it at the end of the resonator. If you couple here the flux qubit by magnetic field, you need to couple it in the middle of the resonator. The other type of resonators which are more compact and also very frequently used is the so-called notch port coupled resonator. Simply, it's a resonator which is grounded. But because by grounding, you make two ends of resonator in different boundary conditions. So one is open, which means that they corresponds to the maximum of the electric field amplitude. And the bottom, which is grounded, corresponds to the maximum current flowing there. So it's actually antinode of the magnetic field, AC magnetic field. The wavelengths, the resonator fundamental mode corresponds to the wavelengths which is 4 times larger than the length of resonator. So it's a so-called lambda by 4 divided by 4 resonator, which actually, of course, also leaves enough space to couple the transmon qubit at the open end here, and the flux qubit, if you want, you could couple it in the maximum of the electric field. And these resonators, they operated typically at frequencies of, let's say, in the range of between 6 and 8 gigahertz. This is kind of favorite choice very often. Then this corresponds to the wavelengths in vacuum of the order of a few centimeters. And if you have silicon as a substrate, then of course you have to divide these wavelengths roughly by square root of epsilon plus 1. For silicon, epsilon is about 11, so it's a factor of roughly 4 or maybe 3.5, a reduction of the wavelengths. So you need to put this resonator on chip, and this requires some space. So typical readout resonator sketch is shown here. So you see this meander type resonator basically is drawn here to save space on chip. And on one end it's grounded, on the other end it's open. So this is this notch port coupled resonator, which is actually capacitively coupled because it's open end. Here is capacitively coupled to the transmission line on top here. And this ways of coupling resonators has an advantage that one can use a transmission line, single transmission line, and then multiple resonators at different frequencies. And then by deciding at which frequency we want to measure, we decide about which qubit we want to measure. And moreover, we can synthesize a signal consisting of many frequency components, and with one pulse of this signal, we can read out multiple qubits. And this is how it's done actually with modern quantum computing circuits. This technique is called frequency division multiplexing, and the typical setup would have multiple resonators coupled to individual transmission line. This slide I already shown, just reminding you this actually was done about 10 years ago for the first time in our lab in Karlsruhe, but then was fully accepted by all the community and is being kind of standard these days around the world. Now, what are the limitations of this multiplexed qubit readout? One limitation is the so-called frequency crowding. Each resonator has its own quality factor, and if you want to put several resonators at close frequencies, you need to make sure that those resonators do not really interfere with each other, their line widths do not interact, and their dispersive shift actually is smaller than the distance in frequency between the frequencies of resonators. Another even more important limitation is the saturation power of input amplifier. And the amplifier which is being used to amplify this very weak signals of few photons in the pulse are very low noise amplifiers, which are consisting of parametric amplifiers, superconducting ones, and semiconducting cryogenic amplifiers. I will explain a little more about parametric amplifications a bit later, but it turns out actually that the saturation power, which means the range of linearity of the amplifier, is not that large. In particular, for parametric amplifiers, is only let's say around 20 dB. So you cannot amplify arbitrary large signal. If you need more resonators, you need more power of your signal of different frequency components. And of course, the amplifier will get quickly saturated. So this is a natural limitation for the multiplex qubit readout. Another limitation, of course, is the topology of the circuit. You need to put this transmission line such that you could have input and output, and this transmission line is not interrupted by any other circuit elements. Now, I mentioned very briefly that there are two types of measurements. There are measurements measuring the large signal, where you do basically you measure a projection of the qubit state to the z-axis, or maybe other axis, depending on your rotation, which you do before the readout. And there is also a weak measurement, which actually gives useful information about the qubit, but it does not make the qubit fully collapse. So these are techniques which are being used in different types of experiments, and both are validated and work very well with superconducting qubits. Now let's talk a little bit about amplification of the signal. In general, if you have a signal with very few photons, and you know that that's what we have seen here, let me go back maybe quickly to this Hamiltonian. Once you have photons in the resonator, then the qubit is shifted in frequency, and every photon will shift the qubit by this amount here. So to have a smaller shift of the qubit, and therefore a smaller back action of on the qubit, you have to use very few photons in the measurements, and very few photons means very weak input signal. In addition to the input signal to the amplifier, which measures the state of the qubit through the signal in the resonator, you always have input noise. And once you amplify the signal, but you also amplify the noise. And in addition, you add an additional noise, which is the added noise of the amplifier. So any amplifier, except for ideal parametric amplifier, they will add some additional noise. And this noise is characterized by the noise temperature. So one can write the conventional Johnson-Nyquist noise spectral density, power spectral density. And in the matched load, it is, as a function of frequency, is flat. And once you have the temperature, which is much smaller than the frequency, then one has to take into account the quantum noise, which is basically due to the statistics of fluctuations. And also, we know that this noise will contribute as a function of frequency to the noise of real devices. Now, the effective number of photons at in the signal can be counted simply by dividing noise spectral density by the photon energy. And then the amplitude of the amplified signal is simply proportional to the gain. Now, the gain is often given in dB, like 20 dB, 30 dB, and so forth. This is a relative logarithmic scale gain, and it's referred to the power. And therefore, once you talk about the voltage amplitude, the input and output, then you have to take a square root of this gain, because power is proportional to the square of the voltage. The effective noise temperature can be also characterized in particular number of noise quanta, noise photons, which present in the signal, and that's basically dividing the power noise spectral density, dividing by energy of individual photons, which gives you the number of noise photons. So the noise in the measurements is given by the product of the effective noise temperature, which is KBT, times the gain of the amplifier times the bandwidth. B is the bandwidth in hertz. So if your amplifier simply amplifies a very narrow range, of course, you can shrink the B, you can make it very narrow, so total power will be smaller, but you will not be able to see the other parts of the spectrum. So if you want to have a broadband amplifier, you unavoidably increase the noise proportionally to the bandwidth. There is a very important consideration which physicists do not really always know. Electrical engineers know this by heart, know this really very well, but that's something which is very important for experiments with superconducting qubits. And the outcome of this simple calculation of the contribution to noise of a chain of amplifiers with different number of noise photons added to the signal, the bottom line is that the most important is the lowest noise of the front-end amplifier. So this amplifier is the most important because it gives the largest contribution to noise. And if you go through this calculation, you can easily see that the total gain of the system is given by the product of the gain of 3 amplifiers. So this is power gain G1 times G2 times G3. This is the gain of the system. While the number of noise photons which are added to the signal is the most crucial for the first amplifier. So here you have the noise photons contributing directly to the noise of the whole system, while the noise of the second stage of the amplifier is divided by the gain of the first stage, and the noise number of noise photons of the third stage of the amplifier is divided by the total gain of the part of the circuit before this stage. So basically, the signal to noise ratio is determined by the input power, which you apply to this chain of the amplifiers, divided by the number of photons in the bath and in the system, and divided by the bandwidth. So larger is the bandwidth, smaller is the signal to noise ratio for the same signal strengths. Now, for single shot measurements, single shot means that by doing a single measurement, you would be able, with a high fidelity, measure the projection of the qubit state on the z-axis. And single shot measurements basically are they require very low noise temperature of the system, and they require also the special coupling of the qubit to the readout resonator. So you need to, of course, to couple the qubit strong enough that it's not that's well coupled to the resonator to measure the qubit state. On the other hand, you don't want to couple it too strong because the resonator will influence the coherence time of the qubit, and that's kind of trade-off which one actually always considers here. Now, picture on the left shows you the single measurement trace of the voltage output of the amplifier. And then if the qubit is in the state 1, you see the blue trace. If your qubit is in state 0, so 0 is blue trace and 1 is the red trace. Now, if you do many averages, then what you show that you go from state 1 to state 0. For example, if you excite by pi pulse the qubit from state 0 to state 1, then the qubit will slowly relax from state 1 to state 0, and therefore the contrast will decrease. So the largest contrast is basically in the beginning of this pulse, and that means that you want to couple the qubit strongly to be able to measure in a short time in order to discriminate the state 0 and state 1 of the qubit in the readout. So in this particular example, noise, the system noise temperature was of the order of 7 Kelvin, and you see that after only 1 microsecond, actually, it's very difficult to distinguish state 0 and state 1. Now, what helps here a lot is the phenomenon which is called parametric amplification. And you guys know this, of course, very well from daily experience. If you sit on the swing, on the kachelях, and you decide to increase the amplitude of oscillations, then you move your legs such that there will be twice the change of the position of your center of gravity per period of the oscillations. So the parametric oscillation here is that you change the length of the pendulum, and if you do it twice per period of oscillations, then you can pump the energy in the pendulum. This is a mechanical problem which you, of course, have heard in mechanics, and very similar thing occurs also in electrodynamics. For example, if you have an oscillator as a pendulum, you need some non-linearity. So if you have an oscillator which frequency you can control, then you could also excite oscillations in the system. And imagine that you have here an LC resonator where you would be able to change the inductance of the resonator during the oscillations. And once you have the charge here in the bottom, then of course you cannot excite it. But if you displace the charge a little bit, make the capacitor charged, then by manipulating the inductance with the frequency, which is twice the frequency of the oscillations in this resonator, one can basically provoke the oscillations and make the power of the oscillations increase. Similar happens, of course, in the tube and so forth. Now, the parametric amplification is a process which is driven parametrically, and it's not dissipative. So, of course, the dissipation may occur, but in principle, the simplification is due to, in a way, dispersive process, which depends on frequency, and which actually has its own characteristic, which basically are spectral and non-dissipative. Извините, я заметил, что я проскочил время, когда должен был сделать перерыв. Давайте все-таки сделаем перерыв тогда сейчас. Вот, прервемся, потом начнем с вопросов, если у вас появились по редауду. Вот. А дальше уже будем говорить. Извините, что-то я задумался, там заговорился. Так, сейчас у нас 4 минуты первого, поэтому давайте мы встретимся с вами давайте в 15 минут. Первого вы можете отдохнуть, выпить чашечку кофе. Я сделаю то же самое. Вопросы после перерыва. Давайте продолжим. Пожалуйста, вопросы какие-то появились по части считывания кубитов по редауту?
А вот можно спросить, там мы в самом начале говорили про пропускание. Вот, я не особо понял, что это такое.
В начале вот здесь вот, да?
Да, в самом начале. Ну, вот чуть дальше. Вот, да.
Вот это?
Ну да, здесь либо на предыдущем.
Либо эту?
Да. Как я понял, это плюс-минус одно и то же. Ну, то есть, если...
Ну да, вот эта картинка – это тот резонатор, который обсуждается вот на предыдущем слайде. Здесь, в принципе, два сдвинутых состояния вот эти вот есть, да? И в чем вопрос?
Вот что такое пропускание?
Это амплитуда и фаза сигнала, который проходит с левого порта на правый порт.
Ага.
То есть, если мы находимся в резонансе с вот этим вот участком, то у нас амплитуда максимальна. Ну и как бы величина сигнала передаваемого максимально. То есть, когда у нас находится здесь резонатор, который вот так вот вставлен в линию, как только мы отстроились по частоте, то, естественно, мы не возбуждаем здесь колебаний, поэтому прохождение сигнала очень слабое. А дальше сама частота вот этого резонатора, она изменяется в зависимости от состояния кубита. Она вот либо здесь, либо здесь. Этот сдвиг очень маленький. Это обычно несколько мегагерц или там пару десятков мегагерц при частоте колебаний порядка нескольких гигагерц.
Хорошо.
Вот. А вот на следующей картинке, это вот важный вопрос. Видите, здесь не пик, а провал наоборот. Потому что если мы меряем отраженный сигнал, то как раз в резонансе у нас сигнал не будет отражаться, он будет проходить насквозь в землю. Видите? Вот. Поэтому здесь как раз отраженный сигнал, он, ну, так, вот, если он меряется вот таким вот как бы резонатором, как это по-русски называется, absorption coupled иногда его называют, или notch. Ну, в общем, такой резонатор, который фактически через емкость связан с Землей. Тогда на частоте резонатора вот этого у нас прохождения сигнала по линии не будет, а наоборот, если мы отстраиваемся по частоте в сторону, то получается полное прохождение. Тогда у нас как бы никак не влияет на наш проходящий сигнал наличие резонатора. То есть есть два как бы способа, ну, две конфигурации включения резонатора. Меряется либо большой сигнал на маленьком фоне, либо маленький сигнал на большом фоне. В разных ситуациях удобно либо одно, либо другое. Еще вопросы, пожалуйста. Okay, let's continue talking about parametric amplifiers. So the way parametric amplifier works is actually very simple. Suppose you have a nonlinear microwave resonator, which can be simply a transmon qubit, can be anything. Typically, you would have some inductance formed by Josephson junction and some capacitance, which is in parallel. And then once you have the input signal, which you apply here, this is a small signal which you apply on the left. In addition to the signal, to make the amplifier work, you need to apply also the pump signal, which may, generally speaking, have a frequency different from the frequency of the signal. Can be close, can be twice larger, and principal can be arbitrary signal. And then at the output, you of course have some pump signal, which is propagating further. But in addition, you have the amplified signal, which is simplified a bit larger, and another one, which is called idler. in Russian, idler is called зеркалка. То есть есть сигнал, есть зеркальный сигнал по отношению к накачке. This symbol here, this kind of circular arrow is showing the device which is called a circulator. This device basically promotes propagation of signal from left to the bottom without transmission through, and then reflected signal from the resonator propagates to the right. And then if the signal is reflected from the output, it will go to the input. So this is a non-reciprocal device which is used to direct microwave propagation in microwave electronics. If you have simply here a Josephson junction, then a Josephson junction behaves as a nonlinear oscillator, and its property is such that if you have the resonance frequency of the junction, which is the frequency of the oscillating pendula in its mechanical analog, and then you start driving these oscillations, and your driving frequency can be either the same or different. If it's the same, then you're exactly on resonance. You are here at zero shift from the resonance frequency. However, if you detune, then you may have, of course, the reduction of the amplitude of oscillations. And if you increase farther and farther the driving amplitude, then the amplitude of junction oscillations will have rather peculiar dependence on frequency. First, if you increase the oscillations farther and farther, the anharmonicity, which is a soft anharmonicity, will influence the amplitude of oscillations. So there will be a modification of this Lorentzian peak, which you see as a blue line, into green, and furthermore this violet line, and so forth. And as an extreme case, if you really drive the system very hard, you drive nonlinear oscillator very hard, then you have the instability point, which actually makes two states possible stable. One state with high oscillation amplitude and one state with low oscillation amplitude. Moreover, the phase in the resonance changes as 2 pi. So if you switch from one state to another, there is a very abrupt and very sharp change of the phase of the oscillations. This is now the amplitude, and this is the phase. And this device was actually used a lot as a so-called bifurcation amplifier. In a way, it's kind of comparator, which discriminates between the oscillating states with different phase. So for the same frequency and the same driving amplitude, basically you have two solutions due to this hysteretic nature of the operation of the nonlinear oscillator. And if one plots the amplitude of the pump here as a function of the frequency, this is a real data measured on Josephson junction. Then here you have the frequency in gigahertz, which is depending on the frequency of the power of the driving field. Then the color here is the phase. So as you go from left to right, the phase changes by 2 pi, and that's where actually the previous picture where the top of this peak is observed. So it shifts to the right. But then if you do it more and more, then you have this multi-stability. That's why you have the bifurcation regime. And somewhere here, before the bifurcation regime occurs, you have a very sharp edge of the peak. And that's where the parametric amplification actually is operating. So basically, parametric amplification is the most efficient at the point where the response of the nonlinear oscillator is extremely strongly depending on frequency of the drive. And that's where a tiny addition of the signal to the pump will make the output varying very strongly, and the spectral components will be both the pump and the amplified signal and the idle, as I described. So that's actually quite interesting nonlinear phenomenon, which has been, of course, discussed in a variety of different systems. You can read about this in mechanics in volume 1 of Landau-Lifshitz. You could also read about this in various books about electrotechnics. Actually, it's also the way to pump to amplify optical signals, and parametric amplification is also very common in optics and quantum optics. Now, how does the parametric amplifier looks like? Well, it's in principle it's just a box which has several ports, and the signal which will be reflected from this amplifier goes in one port, and the signal which you apply as a pump can go in the same port or in a different port. And then there are, of course, some control ports, which can be, for example, port controlling the Josephson junction plasma frequency, which means the operation frequency of the amplifier. This can be done by replacing the junction by a squid. And then this device is basically a large Josephson junction, which is oscillating under the effect of the external drive, and adding the small signal to this oscillation state of the junction actually makes it possible to amplify small photon number signal. Now, when we measure the qubit states, we want to distinguish the states with different phases. And as I explained to you, these phases are usually extracted by using the IQ mixers. I and Q in phase and quadrature, I for in phase, Q for quadrature. The I and Q actually are the terms which are generally used in simple picture. I is the amplitude, Q is the phase. But since there will be always some additional phase accumulated in the device, the only thing we need to know that these two signals are shifted by phase by pi over 2. So if you have I, this will be, for example, sine of omega t. If you have Q, the amplitude is going to be cosine of omega t. And then if we plot the signal on IQ plane, then the general presentation of the signal will be such that we have certain amplitude and certain phase. So in this case, we will measure some particular point at IQ plane, and the qubit state states blue and red will be characterized by two blobs. One blob will be, of course, blobs because you have all this noise. So it's not a single point, it's sort of smeared point for each state. And the quality of the readout is characterized by the size of this blob. So if you have a very small noise, then you have very easy discrimination between state 0 and 1. But if you add a noisy amplifier, then this blob grows because you have amplifier added noise, and the other blob grows, and then you have the overlap between those two areas. And then if you count points in this area above, this will be state 0. If you count the points in the area below, this will be state 1. But in between, there will be some points in between, and these points will be lost if the blobs are too large. So basically, you need to find a way to kind of separate those states. Easy way to separate them is, of course, apply larger signal. So if you bring this vector of large amplitude, you move the states far away, but large amplitude will have the back action on the qubit. So this readout will now unavoidably make the qubit less coherent. And there is always a trade-off to having sufficiently large signal to have good signal to noise ratio. On the other hand, the qubit has to be left as little influence as possible in order to make it quantum coherent and convenient for doing the computation. Now, how are the qubit measurements done? So far we did not discuss much of the experimental facts, but in reality, of course, you need to bring the qubit to very low temperatures. And these low temperatures are in the range of millikelvin. As we discussed, we need millikelvin because 1 gigahertz is 50 millikelvin. So if you want to have transition frequency of few gigahertz between 0 and 1, we need to have the thermal fluctuation energy kBT being much smaller than h bar omega between 0 and 1, omega 0, 1. And therefore, most typical temperature which is being used for qubit measurements is in the range between 10 and 20 millikelvin. Now, when we bring the signal from room temperature electronics, the signal has to contain as little as possible thermal photons. And moreover, we don't need large signal, we need only few photon signal applied to the qubit. So therefore, on the way, typically people place many dividers, which are called attenuators. Basically here, like 30 dB or 29 dB of power is going to the ground, and only 1 dB is going through. And then this division of power between the power dividers at different temperatures basically leave only few photons of useful signal and bring all the noise, which is certainly smaller than the signal at room temperature. The noise photons, they all go to the ground here. So only few photons of useful signal are left. And then the output signal from the qubit goes into the amplification. And then of course, there is a resonator here shown as a box. I don't discuss detail, but this is a signal, actually readout signal, which actually contains information about the state of the qubit through the state of the resonator. And then this first stage application is achieved by parametric amplifier, which is also placed at lowest temperature. After that, there is an isolator, which is basically a circulator, which I explained already, having two ports, and the third port is connected to 50 ohm load. In this case, there will be only non-reciprocal transmission between the two ports. This is needed in order to avoid reflection from the next stage of the amplifier, to have the back, which will have, of course, a kind of back action on the qubit. That's something you don't want. And then the second stage amplification is typically done with 3 Kelvin amplifier, which is a HEMT, high electron mobility transistor amplifier. And finally, there is a room temperature amplifier, which is used to amplify the last portion of the signal. And then using the same reference signal, which we applied to the qubit, we mix the this reference local oscillator signal with the incoming signal from the qubit, and then extract I and Q, the two quadratures, which we digitize then, and then plot on this IQ plane. And if the states 1 and 0 are well separated, then of course we have a single shot contrast, which allows for high fidelity qubit readout. Okay, a few more slides about Johnson parametric amplifiers. I think we do not really have that much time to discuss this, but to say things briefly, the favorite regime of operation of the amplifier is the so-called three photon regime, where frequency 2f is applied to the amplifier, and then the signal has a frequency which is close to f, and the idler has a frequency which is 2f minus f, or minus f signal, sorry. Then basically you have the pumping at twice the frequency, similar to the swing. There is also a three-wave mixing, which is slightly different. You basically mix the signal into signal plus idle using the second harmonic of the pump which you apply. So in this case, the pump frequency is close to the frequency of the signal, but of course mixing happens because of the presence of the second harmonic in the converted pump signal. So now, parametric amplifiers are phase-sensitive devices. That means that one can use them also to prepare non-classical states of lights. So basically, we are talking about the light field with many photons. However, we can form quantum states of light by massaging, so to say, the coherent state. Coherent state is simply a round blob, which will occur on the IQ plane. But however, one can make a phase-dependent gain, and then at the price of the amplitude amplifier added noise in the other quadrature. So one can reduce noise in one quadrature and then get the larger noise in the other.
And in this case, one basically can generate the amplification of the quantum noise, amplification at the quantum limit. So by choosing the squeezing in a particular direction of IonQ. That's a whole field which is rather interesting. This field is called continuous wave quantum communication or quantum state transfer, and being really significantly advanced over the last years with development of superconducting electronics due to very high ability of squeezing of superconducting devices, very large nonlinearity, which actually allows to achieve squeezing to a degree which is much larger than anything achieved with optical photons before. So by using high contrast readout, one can also observe the so-called quantum jumps. And these are basically measurements which are done due to the ability to discriminate individual quantum states on a time scale which is significantly shorter than their energy relaxation time. Of course, by measuring the quantum jumps, you have the back action of the qubit. So you cannot really measure a quantum system without influencing it back, but this back action can be effectively kind of characterized by a shift, by a phase shift, which is acquired due to the interaction with the measurement circuit. But this interaction is so weak that this interaction does not lead to collapse of the quantum states. So basically, you're not measuring the projection at once, but you are doing the weak measurement of the state, which actually remains a quantum state and evolves in time according to the quantum trajectory. Now, in order to minimize the discrimination between the quantum states, one can use special procedures, which I think I'm not going to discuss in great detail, but there is an interesting approach of doing quantum non-demolition readout, so-called QND readout, where you really do not collapse, but to make a very weak measurement of the state by actually playing between the kind of doing the game between the strengths of coupling and the sensitivity of the readout, which would in a certain protocol would allow to make transition from a weak measurement to projective measurement and back, depending on the increase of either the number of photons or the time of measurements. So that's something, if you are interested, you could look up this work of Ivan Tokmakov, actually only 2 years ago. He published a year ago. Now, parametric amplifiers, there are many of them. And one of the simplest and standard examples is the amplifier, which contains a resonator with a squid coupled to it. So the resonator basically operates as a musical instrument, as a trombone. You know, trombone, when you play, you change the length of the tube, and basically the squid adds extra inductance to the resonator. By changing the inductance, you change the length of the resonator, so to say, and therefore you create a sound like trombone does it you vary the sound by the length of the tube. This was historically one of the first parametric amplifiers. However, its disadvantage is that it's extremely narrow band, so its band is limited by the quality factor of the resonator and can be tuned only by changing the flux in the squid, but its momentary bandwidth is very narrow. This topic is actually very interesting. Using this kind of amplifiers, one can observe very general effect, which is called a dynamical Casimir effect. You know, Casimir effect is the effect of generating photons from vacuum by moving a mirror. So if you have a mirror which can perform a relativistic motion, which means motion with the speed which is comparable to the speed of light, then it can generate virtual photons. And if you have two mirrors, then you can basically have the Casimir force, which will attract mirrors together for the reason that you have only limited number of modes between the mirrors and all possible modes outside. So this is due to the light pressure and something which is very interesting was discussed in different contents also in quantum optics. Now, using the this resonator and a squid couple to it, actually people have demonstrated dynamical Casimir effect such that basically you generate entangled photons at frequencies below the frequency of the pump, such that the corresponding photons will have the frequencies which in sum will give the frequency in the pump. So in a way, it's similar to the parametric down conversion, which is done in optics when you irradiate a nonlinear crystal by light. And then in this nonlinear crystal, there is a process of generation of two photons, entangled photons of half the energy of the pump, which are actually having the frequency in sum equal to the frequency of the pump. So very important development in the recent years for the field of superconducting qubits was the development of the so-called traveling wave parametric amplifiers. Here you have not a single resonator, but you rather have a transmission line. And in this transmission line, you apply a pump, and you also apply, and then you generate amplification of the signal. The problem is, as the signal gets amplified, it will also generate the idler and Zerkalku, and then they both would influence nonlinearly on the elements in the circuit. So in order to amplify with a sufficient dynamic range, one has to tailor the inductances or capacitances of the transmission line in order to match the condition of the parametric amplification. And this condition is, I think I don't have the formula, maybe I do have it later, but something which is also known from quantum optics, that you have to match not only the frequencies, but also to match the wave numbers of the propagating waves in order to make the waves propagate and not having the standing waves. The typical gain versus frequency curve of the traveling wave parametric amplifier is shown here. So you see it really has a band of which is can be several gigahertz. Now this window here is due to the pump. So the pump can be applied either at this frequency or at twice the frequency, which means at around 14 gigahertz. These traveling wave parametric amplifiers have been developed now to the degree that they became basically a standard component for using them together with superconducting quantum processors for reading out superconducting quantum bits. Now, a little bit more about the experimental setup. So in reality, if you want to measure a superconducting qubit, as we already discussed, you need to couple it to the resonator with coupling coefficient G, which depends, of course, on the strength of this capacitor, on the size of this capacitor. But in addition, in order to avoid the relaxation of the qubit in the environment, it's also very practical to use an additional, much wider bandwidth resonator, which is called a Purcell filter. This Purcell filter basically will have the frequency range covering the frequency range of this resonator, but cutting up any other frequencies away from it. In this case, the qubit frequency, which will be placed outside the frequency of the Purcell filter, will be very well protected from the effects of the environment, sort of its second order protection, additional to the protection, natural protection of detuned resonator. And then the signal, which will be transmitted into the readout circuit, will basically have smallest possible back action on the superconducting qubit. Well, the technique about forming the pulses and so forth, so this is something I already discussed. So this is the INQ for the measurements. Now, experimental setup for doing the measurements is, as I said, is a low temperature millikelvin temperature setup. The cryostats, which can be used for that, produced by only a few companies in the world. I think the number of companies is handful, only like 4 to 5 can make those machines. They're quite expensive. They're quite bulky. So here you see the inner part of one of the cryostats. The bottom plate here is the plate which temperature in operation, which means when everything is evacuated in vacuum here, is at about 20 millikelvin. Then here you see a chain of heat exchangers. That's where the helium-3 and helium-4 mixture circulates here to make the cooling procedure at the mixing chamber. The mixing chamber itself is this little cylinder here below. And then the upper plates here are all plates with higher temperatures. This is about 1 Kelvin. This is about 4 Kelvin. So at 4 Kelvin, you also have this HEMT amplifier, which is being used to preamplify the signal. And of course, you also need this high frequency electronics, which is quite bulky and expensive to operate. Even a single superconducting qubit, you need a number of expensive and interesting high frequency devices. Now, there's been quite significant progress in development of integrated microwave electronics using the so-called FPGA. FPGA stands for Field Programmable Gate Array. In Russian abbreviation is PLIS. So these are electronic circuits which are reconfigurable processors, and they are not just having the rigid architecture of a microprocessor, but this architecture can be reprogrammed by the software, reconfigured. And they often contain also service circuits such as AD and DA converters, analog digital, digital analog converters. And they can basically encode very efficiently encode the waveforms to control the qubits, and also one can program these devices to make a very quick recognition of the qubit readout states in the IQ plane. So this is the electronics which does not require transfer of measured signals to large computers, which of course will be very slow, and which is also very interesting, for example, to make a quantum feedback. So if you want to measure the quantum system and then correct the quantum state, one can measure quantum jumps and then follow them and provide the signal back to make the quantum feedback. Of course, this is a technique which is only partially preserving the quantum state due to the no cloning theorem of quantum mechanics. But nevertheless, this technique is very powerful and very useful, in particular if you want to measure multiple qubits in a large processor. So this is a direction of development of the service electronics, which takes place nowadays. Experiments with superconducting qubits, they require a variety of microwave components. You see these coaxial cables. So these are plates here, which I already mentioned in the previous illustration. These are cables which bring down the microwave signals. Now the cables contain also attenuators, which basically are dividers of the power between the signal line and ground. They are mostly needed to avoid thermal microwave photons from high temperature stages. To close the noise in uninteresting frequency range, one uses also microwave bandpass filters. To provide DC signals in the coaxial cables, one can use so-called bias T. That's basically an inductor which connects to the central wire of coaxial cable. One use Josephson parametric amplifiers or traveling wave parametric amplifiers. One use cryogenic high electromobility transistor amplifiers. So all this kind of Lego box to build a setup for measuring superconducting quantum bits is rather advanced and really requires a lot of knowledge about low temperature engineering and physics, and also in microwave electronics. So this is the summary of the part which I wanted to tell you concerning the readout. The bottom line is the qubits are read out dispersively by coupling them to specific resonators of specific frequency. Now, this procedure makes it possible to do the single-shot measurements. And this particular goal requires very low noise, which means parametric quantum limited amplifiers. Quantum jumps, which can be measured, they discriminate quantum states on the time scale, which is significantly shorter than their energy relaxation times. I told you a little bit about jaws of parametric amplifiers, traveling wave parametric amplifiers, which is a kind of subclass of parametric amplifiers. And well, last few slides were just to impress you how interesting and sophisticated can the integrated microwave electronics look like, which is required for measuring superconducting qubits. I should mention that in Russia, we have 3 laboratories where this kind of measurements can be done, maybe 3.5, so to say. So 2 major laboratories are at FISTECH and PSIS. At FISTECH, this is a lab called Artificial Quantum Systems Lab, led by Professor Oleg Astafyev. At PSIS is the lab Superconducting Metamaterials Lab, led by myself. There is also a group at Bauman University working in collaboration with Dukhov Institute on the fabrication and also on experiments with superconducting qubits. So there is a whole program of developing superconducting qubits in these locations. Any questions to this part of the lecture? Я хотел бы еще немножко вам рассказать про текущее состояние дел в мире, но если есть вопросы по считыванию, задайте их, пожалуйста.
Ну, у меня вопрос не совсем по считыванию, но вы упомянули бестабильность, которую можно исследовать в том числе в сверхпроводниках. А есть какие-то недавние работы по бестабильности в сверхпроводниках? Я просто с оптической бестабильностью знакома, а в сверхпроводниках нет.
Нет, здесь бум был примерно лет 10 назад, где вот, видите, этот вот обзор как раз именно по бестабильности. Вот вы можете посмотреть его. Обзор это из Ельского университета, группа Мишеля Деваре. Вот, но, значит, бестабильность, она, в принципе, здесь довольно подробно была изучена. Просто оказалось, что использование вот бестабильного этого усилителя, ну, просто немножко более сложное, чем использование параметрического. Поэтому сейчас, вообще говоря, вот в реальных приложениях как-то все отошли от вот этих бестабильных усилителей. Вот, но подробный обзор, вот и картинки, как раз я, которые я вам показывал, они взяты из этой работы, поэтому все, что сделано, вот вы можете посмотреть там подробно.
Спасибо.
Еще вопросы, пожалуйста. Ладно, у нас еще остается минут 25. Давайте я вам немножко просто расскажу. Как бы это та вещь, которая не будет, я не буду ее спрашивать на экзамене, но просто для немножко так, общего образования хотел бы вам рассказать, может быть, даже и не по-английски, а наконец-то по-русски, как-то уже надоело долго говорить по-английски, про то, что происходит в мире со сверхвходящими кубитами. Сейчас я возьму, расшарю еще один файл. Так, ну, надеюсь, видно. Значит, ну, это вот та лекция, которую я вам не успею прочитать. Я просто немножко хочу вам рассказать чуть-чуть про это, про, собственно, то, что происходит в мире. Значит, то, что произошло, вот самое главное за последние 10 лет, это то, что вся эта область такой науки интересной и физики, вдруг неожиданно стала инженерной дисциплиной, появилась там целая дисциплина, называемая квантум инжиниринг. Все это произошло, на самом деле, довольно резко. И вот, ну, с моей точки зрения, вот, поворот был самый главный тогда, когда научная группа профессора Джона Мартинеса из Университета Калифорнии в Санта-Барбаре в полном составе практически перешла под крыло компании Google. Вот. Это произошло тогда, когда они сделали цепочку из 5 кубитов. Мне Олег оставьте, но потом ему позвонил. Вот. Значит, как раз вот он лег на помине. Вот только что вот такую цепочку, кстати, исследовали значит, коллеги в группе Олега Астафьева на физтехе и сделали довольно интересный эксперимент. Но вот эти эксперименты, в принципе, делались, как вы видите, в группе Джона Мартинеса уже 8 лет назад. Вот. И фактически то, что они показали, то, что можно достигать очень высокой точности двухкубитных вентилей. Когда это произошло, началась действительно большая подвижка в этой всей области, и инвесторы стали вкладывать большие деньги, создавать большие лаборатории. Вот. Ну и сейчас это все бум продолжается. Значит, много компаний участвует в этом. Ну, вот здесь, значит, я привел несколько. На самом деле их сейчас уже, наверное, еще не 10, но уже больше 5. Значит, это и Google, это и IBM, это и стартап такой в Калифорнии Rigetti, это и стартап в Европе IQM, International Quantum Machines, это и английская компания Quantum Circuits и другие. Вот. Intel здесь немножко не выдержал соревнования, он уступил IBM и Google и свернул свои работы, которые он разворачивал в Европе, в Дельфте несколько лет назад, они переключились на полупроводниковые кубиты. Вот. Ну и во всех этих местах, в общем, уже существуют процессоры из нескольких десятков кубитов. Сейчас компания IBM в этом году заявила о создании процессора больше 100 кубитов. Ну, их архитектура немножко попроще, чем та, которую выбрал Google. Они, как вы знаете, я вам рассказывал об этом, используют, значит, кубиты фиксированной частоты, не перестраиваемые по частоте, и делают вентили с использованием параметрических гейтов на разных частотах. Вот. Google пошел по другому пути, который дает им возможность сделать очень интересные эксперименты, в частности, эксперименты по корректировке ошибок и так далее. Ну, в общем-то, некие такие немножко устаревшие уже картинки о том, как IBM представила свои компьютеры на потребительском шоу по электронике в Лас-Вегасе, Consumer Electronics Show. Ну и IBM продал уже несколько машин в мире, то есть в Германии, например, купила компьютер IBM и установила, и с ним начали играться люди в Фрунзенском институте. Вот. Но поворот здесь был довольно большой 3 года назад, когда компания Google продемонстрировала квантовое превосходство. Но об этом вы, наверное, слышали уже, это много где обсуждалось. Значит, здесь фактически было продемонстрирована работа 53-кубитного процессора, который сделал довольно практически бесполезную задачу, но тем не менее очень сложную задачу, с которой классический компьютер мог бы справиться там за значительно большее время. Ну, сначала сами люди из Google заявили, что потребуется там 10 тысяч лет, ну, IBM-щики их поправили, сказали, что 2,5 дня, но все равно 2,5 дня гораздо больше, чем 200 секунд. Поэтому, в общем, можно считать признанным, что все-таки вот это превосходство, оно было показано в этом эксперименте. Дальше, конечно, возникает вопрос, как проверять корректность работы квантовых устройств, если сложность того, что они считают невообразимо и непроверяемо на обычных компьютерах. Как жить дальше? Ну, здесь, в общем, много разных направлений существует сейчас. Это использование искусственного интеллекта для квантовой томографии, использование других методов, приближенных методов расчетов классических, которые могут сравнивать с квантовыми какими-то более простыми сечениями пространства Гильберта. В общем, здесь на самом деле огромное направление, которое активно развивается во всем мире и подкрепляется развитием вот этих всех уже настоящих железок, hardware, которые долгое время отставали от теоретических идей. Вот, ну да, конечно, возникает вопрос, как можно масштабировать, делать более сложные, значит, схемы, и здесь приходят на помощь разные идеи, как можно делать топологию схем, как связывать кубиты друг с другом и так далее. Значит, здесь важно, конечно, понимать, что дальнейшее развитие, возможно, уже как бы повторит путь, пройденный классической высокочастотной электроникой. А здесь используется технология так называемая флип-чип, когда на структуру планарную, нанесенную на подложку, кладется другая подложка с какими-то элементами, которые изготовлены на ней лицом как бы к лицу, соединяется при помощи связывающих таких мостиков, которые называются bumps, indium bumps, руководящие мостики. Вот, и здесь как бы часть схемы, которая находится на одной стороне, связывается индуктивно и емкостным образом с другой стороной. Здесь понятно, что нужно будет использовать криогенную электронику, которая только начала развиваться, и, возможно, сверхпроводниковую квантовую электронику, которой, кстати, в России весьма успешно занимается группа Игоря Соловьева в МГУ. Вот. В общем, здесь, конечно, очень как бы много есть задачи на разном уровне. Вот здесь это иллюстрация того, как делается флип-чип. Видите, здесь есть перевернутый чип наверху, qubit-чип, и есть интерпозер. Это чип, который имеет какие-то элементы, значит, смотрящие на кубиты поверхности. И здесь делают очень такие интересные, довольно специальные трюки, вытравливают значит, дырки в кремнии, которые заполняют металлом, и даже при помощи этих дырок делают резонаторы, потому что сделать планарные резонаторы можно, но как бы масштабировать все это, сделать более сложные схемы, становится все сложнее и сложнее. И вот здесь TSV, это называется Through Silicon Via. Это такие протравленные в кремнии металлизированные сверхпроводниковые коаксиальные трубы, которые выходят к кубитам, и при помощи этих труб можно фактически общаться с индивидуальными кубитами в таком двумерном массиве. Вот. Ну, это повторение немножко того, что я уже рассказал. В общем, много разных идей. Конечно, много всего здесь уже как бы не является физикой, скорее является уже такой серьезной инженерной дисциплиной. Я хотел немножко, может быть, поговорить все-таки, как работает реальный большой процессор Гугла. Вот здесь он показан. Значит, один здесь кубит был выколот, потому что он не работал. Вот, значит, ну, во-первых, этот процессор, он использует вот те самые, значит, каплеры, связующие звенья между кубитами, перестраиваемые по частоте, о которых я вам рассказывал. Видите, здесь имеется вот такой центральный кубит, который соединен двумя емкостями, с взаимодействующими кубитами слева и справа, А и Б. И есть емкость, которая находится параллельно. И в этом случае, перестраиваем вот этот кубит, можно силу связи менять, собственно, менять знак и проводить через ноль. Вот здесь вы видите, как раз мерились осцилляции, своп осцилляции между кубитами. Вот в этой точке и в этой точке связь была равна нулю, то есть осцилляции не было. А вот в интервале между ними была связь слабенькой, а вот правее и левее связь была очень сильная, потому что значит, период осцилляции был очень коротким. При помощи вот таких вот, значит, такого связующего элемента команде из Гугла удалось сделать очень быстрые вентили, всего лишь порядка десятка наносекунд, что позволило сделать довольно большое количество квантовых манипуляций за ограниченное время когерентности этих кубитов, которое составляет вот в Сайкоморе чипе порядка 20-30 микросекунд всего лишь. Дальше калибровка квантового компьютера, то есть установки рабочих точек для всех кубитов, является очень трудоемкой, очень трудной задачей. И эта калибровка занимает дни, недели и месяцы. Вот. И вот Джон в качестве примера привел, что вот такая вот цепочка, значит, здесь есть, сначала создается электроника, потом делаются отдельные параметры, определяются параметры отдельных кубитов, затем дальше определяются какие-то, значит, нюансы считывания, оптимальные точки считывания, затем выстраиваются двухкубитные вентили, это уже где-то позже. И вот на каждом этапе, ну, это, в общем, огромные трудные задачи. Там он сказал, что, скажем, вот на этой задаче была сделана диссертация кандидатская одним из его студентов. В общем, это довольно большая сложная деятельность, которая кажется вначале даже неподъемной, но, как говорится, глаза боятся, руки делают. Вот. И это то, что вот, мне довелось, посчастливилось наблюдать в этой области. Я никогда не мог предсказать, что вообще настолько сложно все это может развиваться и достичь таких высот. Где-то лет 15-20 назад это было вообще невообразимо. Вот. Ладно. Значит, здесь показаны измерения, точнее, количество ошибок в случае, когда кубиты адресуются по отдельности, и в случае, когда они адресуются вместе. Вот. И видно, что вот это вот изолированные кубиты, а это когда кубиты манипулируются одновременно. Как бы одновременно меняется состояние, делаются вентили на кубитах значит, на разных чипах. Ну и видно, что вот как бы неизбежно, конечно, дополнительные какие-то ошибки возникают, когда происходит много чего на одном чипе, кубиты влияют друг на друга, и это влияние учесть очень сложно, то есть возникают ошибки, которые провоцируются работой других кубитов на чип. Вот. Ну и ошибки, здесь баланс ошибок, значит, ошибки есть и в однокубитных гейтах минимальные, есть двухкубитные ошибки двухкубитных вентилей, но самые большие ошибки, они связаны именно с считыванием. То есть вот считывание, на самом деле, это то, о чем я сегодня рассказывал в первой лекции, является очень критическим, очень важным этапом, который влияет на точность работы квантовых компьютеров. Вот. Но здесь показана электроника с использованием FPGA, плюс, значит, схем, которые управляют ЦАПами, и, соответственно, эти ЦАПы генерируют, значит, их сигналы трансформируются по частоте в гигагерцовый диапазон за счет миксеров, которые преобразуют фактически, делают преобразование вверх по частоте. Дальше аналогичные миксеры преобразуют сигналы измерительные вниз, которые затем оцифровываются и также обрабатываются на FPGA. Это вот уже считывание, оцифровка, то есть тоже, значит, имеются усиленные сигналы, есть I и Q, и затем цифровщики, они оцифровывают I и Q, и дальше вот оцифрованные профили сигналов обрабатываются при помощи PLIS. Дальше существует, конечно, сложная электроника, которая требуется для управления, то есть на каждом этапе здесь имеется PLIS-модуль, огромное количество проводов, все это похоже на таких осьминогов, увешанных спагетти. Вот. Но как бы понятно, что обычные компьютеры тоже выглядели очень страшно. Во времена компьютера ENIAC, который весил там много тонн и стоял из ламп, радиолампы и переключателей. Вот. Но со временем, конечно, все это упаковывалось в более компактные, красивые формы, и это все еще для квантовых устройств впереди. Вот эта интересная картинка, которая показывает реальные времена, значит, Т1, времени жизни кубитов в цвете. Это вот цифра, это в микросекундах время Т1 на разных кубитах на чипе. А справа это частоты кубитов. Видно, что в отличие от атомов, все, конечно, сверхпроводниковые кубиты, они все немножко отличаются друг от друга. Как говорится, сколько ни делал папа Карло буратин, эти все буратины выходили немножко разные. Вот. Сколько не изготавливаешь кубитов сверхпроводниковых на одном чипе, все они получаются немножко разными. Поэтому ими нужно как бы управлять индивидуально, их нужно подстраивать. Это и является, собственно, содержанием процесса калибровки. Вот. Ну, дальше это вентили, которые использовались в эксперименте по квантовому превосходству. Ну, довольно сложная работа там больше 60 страниц, конечно, ее интересно почитать. Но, в общем, как бы здесь простая мысль в том, что здесь использовались однокубитные вращения и двухкубитные вентили между соседними кубитами. И дальше, достигая определенной глубины, то есть определенного количества циклов, то есть двигаясь слева направо по горизонтали, создавалось состояние очень сложное, которое приводило, значит, всю эту квантовую систему в дальний-дальний какой-то глубокий уголок пространства Гильберта, в которое дойти, как говорится, классическими ногами не представляется возможным. Вот такая забавная штука. Значит, ну, им, конечно, потребовалось доказать, что все это работает правильно. Они это делали за счет того, что делили фактически чип пополам и сравнивали работу половины чипа с классическими вычислениями, дальше убеждались, что все работает правильно. После этого значит, включали связь между двумя половинками и получали уже более сложное состояние. Вот. Ну, наверное, дальше не буду комментировать это все, как раз вот это валидация протокола, так сказать, полная схема, две половинки, вот, и частичная связь. Вот. Ну и видно, что это вот как бы здесь приведено количество лет на классическом компьютере, которые не оценивали по сложности задачи. Значит, важным направлением в развитии этой деятельности являются квантовые симуляторы. Квантовые симуляторы можно, наверное, сравнить вот с аналоговыми компьютерами. Вы, наверное, этого уже не застали, а я в свое время, когда учился на физтехе, мы делали простые устройства, ну, скажем, там, сумматор. Это просто усилитель, который складывает два сигнала. Или там умножитель. Вот. И вот на основе таких электронных устройств, которые были фактически просто там, частично линейными, частично нелинейными элементами, основанными на транзисторах, можно было делать вычисления аналоговые, когда два входных сигнала, скажем, преобразовывались согласно какой-то математической формуле. Вот. Но это время ушло в прошлое. Вот. Но вот с кубитами, на самом деле, в силу сложности задачи томографии для большого количества кубитов, на самом деле весьма содержательным является класс задач, где можно фактически закодировать некий гамильтониан, то есть его параметризовать, как говорят, под конкретную вычислительную задачу. И дальше исследовать эту задачу, которая интересна, манипулируя какими-то параметрами вот в этом искусственным образом смоделированным при помощи кубитов гамильтониане. И здесь существуют задачи, как, ну, например, квантовой химии, где нужно посчитать силу связи там, внутри молекул, так и задачи оптимизационные, так и задачи квантовой физики многих тел и так далее. Вот. И здесь, конечно, довольно много было сделано за последние годы, где были продемонстрированы какие-то простейшие, весьма успешные применения таких вот квантовых симуляторов для разного рода моделей. Вот. Есть целая огромная область, называется она, значит, квантовая оптимизация. И здесь, как вы, наверное, слышали, существует компания D-Wave, которая заявила о том, что все-таки они дают квантовый выигрыш в решении задач оптимизации. Потом это много раз оспаривалось. Ну и сейчас, судя по тому, что происходит с акциями компании D-Wave, дела у них идут не сильно хорошо, хотя они продолжают, в общем, свою работу и были первой компанией, которая вышла на рынок квантовых вычислений. Вот здесь фактически делается вычисления, которые иногда называют адиабатическими квантовыми вычислениями, когда также создается определенного рода гамильтониан с большим количеством параметров, и дальше основное состояние этого гамильтониана изменяется адиабатически за счет изменения параметров. И фактически решением задачи после, значит, заданного изменения параметров является измерение конечного состояния, конечного основного состояния этого гамильтониана. Вот. Но далеко не все задачи, они параметризуемы для того, чтобы можно было делать какие-то полезные вычисления, но тем не менее существует довольно большое количество задач, связанных в том числе с машинным обучением, с оптимизацией, где подобные вот, анализ подобных графов приводит к каким-то полезным результатам. Вот. Ну, это то, что я вам уже сказал. Пожалуй, я пойду немножко дальше. Это вот компания D-Wave, которая продавала и продает все еще квантовые компьютеры, но которые, ну, лишь отчасти квантовые, потому что на самом деле они используют технологии, в которой весь чип, безусловно, не может быть квантовым, используют милловые схемы, где квантовость, она, возможно, существует, но только на уровне ближайших кубитов, а вся большая квантовая система не является когерентной. Вот. Это все D-Wave, их развитие. Вот, значит, ну, последние все-таки несколько минут я хотел упомянуть очень важную, интересную тему. Это коррекция ошибок квантовых. Здесь сделано еще немного, хотя что-то уже сделано, придуманы алгоритмы, которые позволят сделать квантовый компьютер, работающий без ошибок. Это так называемый поверхностный код, который был придуман Алексеем Китаевым и Прескулом более 20 лет назад. В этом поверхностном коде измерения работа делает следующим образом. Берется большое количество физических кубитов, которые заполняют, ну, если угодно, шахматную доску. И вот белые клетки в этой шахматной доске являются физическими кубитами, а черные клетки в шахматной доске являются так называемыми свидетелями. Их иногда еще называют энцилос. И вот эти свидетели, они используются для того, чтобы определять ошибки четности. То есть они меряют состояние кубитов, и в случае, если в одном из кубитов возникает ошибка, возникает сбой, эта ошибка в случае физической ошибки, физического сбоя, она возникнет лишь в одном из них и имеет очень малую вероятность возникнуть в двух одновременно. И в этом случае вот эти вот результаты, значит, эти сигналы, которые измеряют свидетели, по совпадению или несовпадению по четности состояния двух кубитов, они являются такими флажками возникновения ошибок. Дальше эти ошибки можно устранять, ну, либо просто сортировать, так сказать, эти данные, отбрасывать, когда ошибки возникали, брать те данные, которые были получены без ошибок, ну, либо использовать какие-то более сложные алгоритмы, например, кодирование большого количества физических кубитов в один логический кубит. Вот. И логический кубит, на самом деле, будет представлять собой некое такое, ну, в общем, не совсем даже наглядно представимое какое-то образование. То есть это, на самом деле, область, в которой будут набираться, значит, определенные, значит, сигналы этих свидетелей. Вот. Значит, ну, для того, чтобы квантовый, значит, код коррекции ошибок, поверхностный код заработал, необходима вот такая вот, как бы, как я уже сказал, шахматная такая схема. И здесь несколькими группами были продемонстрированы простейшие какие-то измерения ошибок не всех там x, y, z, а, скажем, ошибок только по x или там только по z. Вот. И ну, простейшие какие-то вещи были показаны. Совсем недавно компания Google продемонстрировала на своем процессоре такой, ну, как бы фрагмент алгоритма коррекции ошибок для цепочки кубитов, где глубина коррекции была довольно значительная, и где им удалось показать, что действительно код коррекции ошибок приводит к времени жизни логического кубита более долгого, чем времени жизни физического кубита. Для этого ошибки в физических кубитах должны быть довольно маленькими. То есть в случае ошибок на уровне 10-4 требуется огромное количество физических кубитов, порядка тысяч и даже десятков тысяч, чтобы сделать один логический кубит. Вот. Но если качество физических кубитов растет, то в этом случае для изготовления логических кубитов потребуется все меньше и меньше ресурсов, все меньше и меньше физических кубитов. Вот. Но это вот дорога для error correction, то есть это вот двухкубитные ошибки, показаны пунктиром на уровне 10-2. Вот. И это картинка из лекции Джона Мартинеса пару лет назад, где он показывал, как бы, какое количество кубитов необходимо для того, чтобы двигаться в сторону коррекции ошибок. Вот. Ну, я боюсь, что, конечно, здесь, наверное, мы уже не сможем с вами обсудить, значит, коды коррекции ошибок. Если вы хотите про это что-то узнать, активным человеком, который в этой области работает, является в моей группе Илья Симаков, аспирант 2-го года, закончивший физтех не так давно. Если вам на эту тему что-то интересно поговорить, вот, обращайтесь, как говорится, к терапевту, к Илье. Он вам много интересного может рассказать. Вот. Ну и, наверное, закончу я этим слайдом. Ну, наверное, можно считать, что это общепринятым, несмотря на редкие, так сказать, и такие немножко раздраженные высказывания все-таки всяких других платформ, атомы и ионы. Все-таки сейчас сверхпроводниковые кубиты являются наиболее продвинутой платформой для создания квантовых компьютеров. Это показывает, в общем-то, и количество денег, которые вкладывается туда большими компаниями, крупнейшими компаниями. Вот. Было достигнуто квантовое превосходство. Схема, которая сейчас используется, включает уже более сотни кубит. Вот. Впереди здесь, на самом деле, Google, IBM и китайцы. Вот все эти группы имеют более 50 кубитов. Вот. Вентили можно делать очень быстро, они занимают десятки наносекунд. Времена когерентности выросли сейчас до десяток и даже сотен микросекунд, и это, конечно, позволяет сделать довольно большое количество вентилей за время жизни кубитов. И, в общем, эта гонка продолжается, и здесь много всего интересного. Не факт, что путь, который избран компаниями, о которых я говорил, является единственно приемлемым. В частности, выбор основы архитектуры в виде трансмонов уже себя, видно, что он себя исчерпал. И здесь те работы, которые сделаны у нас в России, в частности, по потоковым кубитам, по флаксониумам, они находятся на очень высоком мировом уровне. На эту тему работают, в этом направлении в альтернативных кубитах работают, в частности, компания Alibaba, которая имеет группы и в Америке, и в Китае. Вот. Но если вам это интересно узнать, в общем, напишите мне, можно легко организовать тур по лаборатории в МИСИС, и, наверное, тоже можно в физтехе, поэтому проявитесь, когда у вас будет время и желание, обращайтесь к нам, у нас есть много тем для работ вот, студенческих. Так что это живая, очень интересная область. Ну вот как-то так. Спасибо вам за внимание. Если спросите чего-нибудь в конце, буду рад ответить на ваши вопросы, если таковые остались. Пожалуйста.
Спасибо большое. Подскажите, пожалуйста, а как будет проходить экзамен и есть ли какие-то материалы для подготовки? То есть я имею в виду там список тем более обширный, чем он был в начале, или какие-то вопросы?
Конкретных вопросов нет. Будет просто разговор с каждым из вас на тему вот этой лекции. Как устроены сверхпроводниковые кубиты, как устроены ионные кубиты, там, как делаются вентили, что такое времена когерентности. То есть такие совершенно общие вещи, которые как бы обсуждались многократно в лекции. То есть они, поскольку нет учебника какого-то устоявшегося по этой теме, есть несколько обзоров, которые я выложил на диск, на котором вы можете посмотреть также все лекции. Вот. Экзамен будет происходить у нас в 2 дня, по всей видимости, потому что очень много народу у вас. Это и МИСИС, и физтех. Вот. И вроде мы договорились с Настей Горяйновой, что экзамен будет понедельник и вторник. Это будет, если не ошибаюсь, 15-16 января. Вот. Какой день вам удобнее, сами решайте. Начнем мы, наверное, часов в 11. И на каждого человека там будет, я думаю, что 10-12 минут. Вот. Просто будут какие-то вопросы, что вы там про это знаете, помните. Видите, просто когда человек начинает говорить на какую-то тему, сразу, в общем, становится понятно, знает он что-то или не знает. Я не то, чтобы хочу вас особенно помучить. Моя цель этого курса, чтобы скорее, может быть, даже не то, чтобы вы выучили какие-то дидактические вещи, а чтобы вы получили представление об этой очень бурно развивающейся такой современной области и физики, и квантовой науки. И чтобы привлечь как-то ваш интерес к тому, чтобы, может быть, вам самим этим какой-то частью всего этого позаниматься. Еще вопросы, пожалуйста.
То есть будет один день сдает физтех, другой МИСИС, или нам надо как-то будет распределиться, кто 16-го, кто 17-го?
С помощью Насти вы все это сделаете, там у нас неравное, поэтому я хотел бы, чтобы там более-менее равное количество каждый день было. Вот. Это Настя вас организует. Вот. Экзамен будет по Zoom.
Про фотонные чипы вы что-то знаете? Я просто помню на первых лекциях. было.
Ну, то, что я знаю, я вот вам рассказал. Я это знаю очень поверхностно, ну, фотонные чипы. Про них, конечно, спрашивать много не могу. Вот. Но, ну, как бы вопрос о том, ну, как кодируется информация в фотонных системах, ну, наверное, хорошо бы вам знать, я об этом немножко рассказывал. Что есть там кодирование в поляризации, что есть фотон, нет фотона. Вот. Ну, какие-то такие вещи, наверное, базовые хорошо бы знать. Как устроены вентили. Ну, они там, однокубитные вентили, это полупрозрачные пластинки, наверное, вы это знаете, да? Но как бы подробно спрашивать про вот как бы не твердотельные реализации я, естественно, не буду, то есть какие-то общие вещи совсем, потому что это было только краткое введение в этом курсе. Вопросы еще, пожалуйста. Ну, хорошо, раз вопросов больше нет, тогда еще раз спасибо всем за то, что приняли участие в этом курсе. Надеюсь, вам было интересно. Вот. Ну и буду рад с вами немножко еще поговорить, чтобы раздать всем, надеюсь, хорошие оценки в январе. Вопрос в чате. Мне спасибо. Хорошо. Спасибо, что написали. Пожалуйста. Ладно, тогда все. Всем хорошего дня.
Да, последний вопрос. А будет ли какая-то консультация?
Ну, не планировал.
Хорошо.
Спасибо большое за курс. Всего доброго.
Спасибо вам большое. До свидания.
До свидания. До свидания.
Спасибо.